In this illustration, we are given a cylindrical container and the volume of this container is capital V and walls are adiabatic. That means there is no transfer of heat from system to surrounding and surrounding to system. Initially, a light adiabatic piston, this is the light adiabatic piston, divide the container in two equal parts. That means this part is V by 2 and this part is again V by 2. In left part, there is n mole of an ideal gas, with adiabatic exponent gamma and filled at temperature capital T. And in the other part, there is vacuum, there is no gas. If piston is released, the gas fills the whole container uniformly. If we release the system, this piston start moving the right direction and come to at this position, at the extreme position of this cylinder and fill the container uniformly. Find the final pressure and temperature of the gas. We need to find the final temperature and pressure of the gas, and in the next part of the question it is given. Now if piston is slowly displaced externally back to the initial position, that means the piston comes at this position, we slowly push this piston and reach to again initial position, right? And in this case we need to find final pressure and temperature of the gas. Right? This is the question. Okay, now let us move to analysis part of the question. Let us analyze first part. Okay, we know when piston is released, when this piston is released, gas expand to this end, this fill the complete container, right? And we know there is no gas in this right part. If there is no gas on the right part, that means the burden by this gas on this part should be 0. And this cylinder is adiabatic. If this cylinder is adiabatic, we have the first law of thermodynamics as Q equal to delta U plus W, right? And here W equal to 0, right? And this is adiabatic, this is again 0. That means delta U equal to 0. That means U initial equal to U final. That means initial temperature should be equal to final temperature. Okay, so let us revise each and every part of this. Okay, this is clear. There is no burden by the gas because this is a simple, you can say, free expansion. There is no burden by this gas. And as we discuss, there is nothing on the other part, right? That means we can say temperature will remain same. If temperature will remain same, that means temperature is constant. This is a case of a sort of isothermal case. And in case of the isothermal case, we know Bayer's law is applicable. If Bayer's law is applicable, that means P initial, V initial equal to P final, V final. And you know, the volume of this become from half to V by 2 to V. That means the pressure will become half, because PV equal to constant, on doubling the volume, pressure will become half. That means the final pressure should be equal to P initial divided by 2. Okay, and we can find the P initial by using the ideal gas equation. We know PV equal to nRT and N is the number of the moles. So here we can write P initial equal to nRT divided by V by 2, because initial moment we have the half part of the cylinder filled, that is volume of the gas initially equal to V by 2. So we got the P initial value. So this is the P initial. Okay, now we can substitute the value of P initial in this expression to get the P final value. That means final pressure should be equal to nRT divided by V. Now let us move to the next part of the question. Next part of the question, it is given, if piston is slowly displaced externally back to the initial position. Now piston move at this position, and what we are doing, we are pushing the piston back to initial position. That means the final volume is V by 2 again. Initial volume in this process is V and final volume is V by 2, right? So let us analyze the second case. Okay, as we discussed, we are displacing the piston back to initial position, and we know the walls of this cylinder is adiabatic. That means this is the adiabatic compression. If this is the adiabatic process, we can relate pressure and volume by the expression PV to the power gamma equal to constant. So here we can write P1 V1 to the power gamma equal to P2 V2 to the power gamma. And here we know P initial equal to, because it is completely filled with the gas initially, so P initial we can write by using the ideal gas equation, PV equal to nRT we have. Okay, that means we can write P initial equal to nRT divided by V, right? V is the total volume. So now we can substitute this value, okay, and V initial equal to V and V final equal to V by 2. So after substituting the value, we can find the value of P2. P2 equal to P1 V1 by V2 to the power gamma. Now V1 is to V2 is equal to 2. That means final pressure should be equal to P1 multiplied by 2 to the power gamma, right? And now we can write the value of P1 equal to nRT divided by V, right? This is the final pressure. Now we need to find the final temperature. Again, it is a adiabatic process, and we know the initial volume, we know the final volume, we know the initial temperature. We can find the final temperature by using adiabatic relation in terms of the temperature and volume, that is T V to the power gamma minus 1 equal to constant. So here we can write T1 V1 to the power gamma minus 1 equal to T2 V2 to the power gamma minus 1, and here T1 equal to T, that is the initial temperature, because when piston was here, temperature was T. When piston moved to this position, that was the isothermal expansion, temperature was remain unchanged. That means when piston was at this position, temperature of the gas in the container was T. So initial temperature is T, initial volume is V, final volume is V by 2, initial. Now we can find the final temperature. So let us substitute this value. Final temperature should be equal to T2 equal to T 2 to the power gamma minus 1. This is the final temperature.